go ahead and put in the pressure. And that's what we're going to use to get our star terms here. And so what you would end up with, if you do your site balance, is you get K times K C2H6 times the pressure of C2H6. And now I have my site term. And what's on my surface? Just hydrogen. And H star is equal to what? KH2 to the 1/2 power times the pressure of hydrogen to the 1/2 power. I'm skipping some steps here, but you get star over H, and that's where this comes from. Because the site balance is just H. I'll show it. L is approximately just equal to H star. And so you have already a star in the numerator. You need to divide through by the number of sites, and so you end up with this, which is equal to all right, so let's check it against what we know. The other thing that we're missing here is what? There's a term here, and what does that term represent? What did we have before? We had a 2 there. Why do we have a 2 there before? Yeah, but why did 2 have to leave? What was it about the transition state that made a 2 there? How many sites does the transition state occupy? That's what we had, and it's 2. So what are we going to, let's assume here, assume that the transition state also requires 2 sites, just like the example that we had earlier. So now I'm going to put a 2 here in the exponent of the denominator term. All right, so let's just check it against what we have. Is this first order in ethane? Yes. Is it inverse third order in hydrogen? No. What is the hydrogen dependence? -1, right? 1/2 squared 1. And it's in the denominator. So that's not what we get. So this is not how the reaction takes place. So there's a lot of different species where we can break the carbon-carbon bonds.
What's the final answer?
We're going to get there in just a second. I just want to do one more sort of generic example here. Let's look at so where does this hydrogen go once we make it? If we're at pseudo-steady state, it means the concentration of hydrogen can't change. So if I make one, where does another one have to leave? Yeah, so I want you to think of this when you make that one, it's the same thing as doing this. Of course, that means that there's a site left behind. All right, all I'm doing is I'm combining the desorption step with the formation of the hydrogen. So this is no longer an elementary step, but it makes things convenient for us. Now let's imagine that I break apart C2H5 in an irreversible step, and I make CH2 plus CH3. I'm going to go quickly here because of time, but hopefully you guys will notice that what's going to happen is, now what did I have to desorb? So again, I had 6 hydrogens. I had to remove how many So here's my transition state. It looks like this. It's a two-site transition state, and it has the composition of C2H5. And then I have, how many other hydrogens? 2 to either side, because it's a two-site transition state. Everybody see that? I'm not drawing what the transition state looks like. I'm just giving you the composition.
I thought C2H5 and C2H6.
This is the transition state for breaking the bond. Remember, it's the transition state that we put on the right side here, not the adsorbed state, but the transition state. That's what matters in our picture over here. So even though ethylene only takes up one site, in order to break it apart, that's why it's important to stay balanced. I have to react it with a second site, and then I make a two-site transition state because my products require 2 sites. Okay, so what has come in from the gas phase in order to make this transition state?
C2H6.
C2H6, not C2H5. I don't adsorb a radical. C2H6. And now I'm drawing 2 arrows up here. The first is going to be from the surface. How many hydrogen atoms do I remove from the surface? 2, which is how many hydrogen molecules? How many hydrogen atoms do I remove from ethane? 1, which is how many hydrogen molecules?
1/2.
1/2. So the observed rate then is K C2H5, or excuse me, 6. I've been doing pressure the whole time. I'll keep doing it. Divided by what goes down here? The pressure of hydrogen to what power?
1 1/2.
1.5. My observations can't tell where the hydrogen came from. Whether it came from the surface of the molecule, I don't know. But I just observed the total amount, so it's 1.5. Again, what did I really need? 3. Where does that come from? How many hydrogens do I have to remove from the molecule if we assume that 2 come from the surface? Again, we need 3. Let's assume 2 from surface, or sorry, excuse me, 2 atoms, 1 hydrogen molecule from surface. So how many are left that come instead from the molecule? 2 hydrogen molecules or 4 hydrogen atoms. Okay, does that make sense? So it's not, I don't break carbon-carbon bonds in ethane minus 1 hydrogen. I break carbon-carbon bonds in ethane minus 4 hydrogen. And what it actually looks like is this. I remove 2 hydrogen atoms from both ends of ethane. I make that thing, CHCH. And this happens through a long series of elementary steps I'm not going to write on the board. But we just remove hydrogens one at a time until you're left with this. And then in the rate determining step, again, well, I'll draw the other hydrogens here just to remind you that it's a hydrogen covered surface. In the rate determining step, we make 2 CHs. So I still had to adsorb an ethane, because that's where that came from. It doesn't mean that it's literally ethane. It just means something that came from ethane. It could be ethane. It could be something that comes from ethane. Either way, I had to adsorb an ethane in order to do the chemistry. And again, we had to remove hydrogen both from the molecule, 2 hydrogen molecules from the molecule, from the ethane molecule, 1 hydrogen molecule from the surface. That's how we get to 3. Are we done at this point? What happens next? I have to make methane. How do I make methane from CH? You just react it with hydrogen one at a time. So 3 steps. You just add the hydrogens back, one at a time, one at a time. So the end result is that in order to add hydrogen to ethane, I first have to remove hydrogen from ethane. It's the only way that it works. You have to remove enough hydrogen that the metal can grab onto those carbons and break that carbon-carbon bond. And then after you've broken the carbon-carbon bond, you have to add a bunch of hydrogen back. All the hydrogen you removed plus 2 more to ultimately go from ethane plus hydrogen goes to methane. We've studied this with DFT, and it suggests this is the mechanism, and that explains why it is that even though hydrogen is a reagent in the system, it's extremely inhibitory to the overall rate. Okay, that's it. I haven't decided what I'm doing Thursday, so just show up. Probably. Yes.